So far we had seen the net EMF of the cell was found in standard condition. Now we will see how to find out the EMF of half cell and a complete cell having two electrodes and two electrolytes separated with an electrode and salt bridge. In the previous cases so far, we had seen that the EMF was found in standard condition in which the concentration of the electrolyte, be it standard hydrogen electrode or galvanic cell, the concentration of the electrolyte like copper sulfate solution and zinc sulfate solution was taken to be 1 mole per liter. But as the concentration changes, then the electromotive force or the electrode potential may also change. So how to relate the change in the concentration or temperature with the electrode potential of half cell or net EMF of the cell is given by Nernst equation. So we'll discuss about Nernst equation today. Nernst equation. In Nernst equation we find out E cell for cell in which electrolyte may not have a concentration as 1 molar. Such kind of cell is called as concentration cell or concentration cell. So Nernst equation is used in case of concentration cell wherein different concentration can be there of electrolyte. So just to revise, we had seen that E standard cell is equal to E right standard minus E left standard. Also, E right is nothing but cathode. This is in our mind now very well. We will not forget this ever. E cathode minus E anode. These all are half cells. E right and E left is half cell, whereas this is net EMF of the cell. This is net EMF of the cell. And whereas these are individual reduction potential. Individual reduction potential. So first of all, we will find out the individual reduction potential for any hypothetical equation, and then later on we will also find out the net EMF of the cell in terms of Nernst equation. Say for example, just like copper 2 plus becomes Cu metal, or zinc becomes Zn2 plus 2 electron. Say let there be a metal which loses n number of electron and acquires n plus charge and goes into the electrolyte and liberates n electron, such that the concentration of the electrolyte here is not 1 molar. Concentration of electrolyte is not 1 molar. In that case, what we will do? In that case, we have to use Nernst equation such that E reduction potential of m n plus becoming m, not standard, because Nernst equation is found out for cases in which the concentration is may not have 1 molar concentration. So this is reduction potential. We always find reduction potential of electrodes because we consider standard hydrogen electrode to be anode, will be equal to E standard of reduction potential of the metal M having N plus valency becoming M metal minus gas constant R into temperature divided by number of electrons gained or lost N multiplied by number of farad of charge exchanged. So 1 farad means charge of 1 mole of electron. So let me tell you about farad a little bit. Say charge of 1 electron, if it is minus 1.6 10 to the power minus 19 coulomb, then charge of 1 mole electron will be equal to Avogadro number multiplied by 1.6 mode 10 to the power minus 19 coulomb. So this will be coming out to be 6.023 10 to the power 23 multiplied by 1.6 10 to the power minus 19 coulomb will be equal to 96487 coulomb per mole. It is considered to be 1 farad. So this is the charge of 1 mole of electron, and natural log ln 1 divided by concentration, whatsoever the concentration of electrolyte may be, initial concentration of electrolyte may be m n to the power n plus. Now we can make this equation easier by writing E non-standard Mn becoming M is equal to E standard m to the power n plus m. This value we will get from electrochemical series, just like we get this 0.34 minus 0.76 volt. Similarly, we can get this value from the electrochemical series. Minus value of R is 8.314 joule per Kelvin per mole. Temperature is 298 Kelvin. Say N could be anything, any number of electron gained or lost, and 1 farad will be equal to 96487 coulomb per mole. If we have to convert natural logarithm to decimal logarithm, means the logarithm with base 10, then we will simply multiply it with 2.303. This is a rule which you have to keep in mind. 1 by Mn plus. Now these all are constant values. If we multiply all these constant values, then our value will come out to be m n plus becoming m is equal to E cell m n plus m minus 0.059. Means if I calculate all these values together, it will come out to be 0.059 divided by number of electrons gained or lost log base 10. We may write or may not write 1 by concentration of the electrolyte. So this is Nernst equation for half cell. This is Nernst equation for half cell. Now how can we find out the net EMF of the cell for a complete cell? So let us take the example of this couple of electrodes and electrolytes, and then we will find out the Nernst equation for a complete cell. Alright, so this was Nernst equation for half cell. Now we will find out Nernst equation for a galvanic cell. Let me make this concept in the form of a question like this. Derive an expression for E cell for cell notation zinc 2 plus xm x, because it is not 1 molar now, separated by zinc, salt bridge Cu2 plus, let its concentration be equal to Y, because concentration is not 1 molar here, we are talking about concentration cell and Cu. So this is anode, this is cathode. So we can write for Cu2 plus, for Cu reducing to, for Cu2 plus reducing to Cu, expression will be E cell equal to E standard cell minus 0.059 by number of electrons gained and lost is equal to nothing but 2. So we'll write 2 log 1 by concentration of Cu2 plus. So this is reduction potential of Cu2 plus becoming Cu. We will always find out reduction potential. Howsoever, if it undergoes oxidation or reduction, we will always find out reduction potential, because in electrochemical series these values are only given. Then let this be equation 1. Now for reduction of zinc 2 plus to become 2 electron and becoming zinc. Here we have, although zinc oxidizes, but we have taken reduction because we have to always calculate in terms of reduction potential. So E reduction potential of Zn 2 plus becoming Zn will be equal to E standard of Zn 2 plus Zn. This could be also written as Cu2 plus Cu minus 0.059 by 2 log 1 by Zn 2 plus. Let this be equation 2. Now we know that this is anode and this is cathode actually. So what we can do to find out the net EMF of the cell, we can subtract anode from cathode. So net EMF, that means delta E cell will be equal to delta E standard cell minus or cathode minus anode. So delta E cell will be equal to equation 2, cathode is equation 1 minus equation 2. So E cell will be equal to, we'll write cathode as it is, E Cu2 plus Cu standard minus 0.059 by 2 log 1 by Cu2 plus minus E Zn 2 plus Zn minus 0.059 by 2 log 1 by Zn2 plus. So now we can open this together and we can write delta E cell is equal to this minus this will be equal to delta E standard cell, which will be equal to 1.1 volt as we had calculated earlier, minus 0.059 by 2 log 1 by Cu2 plus and this minus will become plus 0.059 by 2 log 1 by Zn2 plus. So E cell, what kind of cell? In which Zn2 plus Zn salt bridge Cu2 plus separator Cu is equal to 1.1 volt, or we can write 0.34 minus 0.76 volt, and then this we can take common as minus 0.059 by 2 log 1 by Cu2 plus, and since again we have taken brackets, we will put minus log 1 by Zn2 plus. So this can be written as finally delta E cell is equal to 1.1 volt. This is a constant value which will be coming out to be minus 0.0245, and then if I make it plus, then this will go up. So we can write log Zn2 plus by Cu2 plus. So in this way the value can be found out. Further, it can also be done like this: delta E cell will be equal to 1.1 volt minus 0.0245 log value of Zn2 plus was equal to x and that of Cu2 plus was equal to y. So in this way the Nernst equation is used to find out the net EMF of the cell in which the concentration is not equal to 1 mole per liter always. So as numericals will come, we will be putting these values in these equations and we will be solving for various types of electrochemical cell. That's it. It's a very important topic, by the way, very important. Try to derive it once yourself. Try to derive yourself now. In our previous introductory discussion about electrochemistry, we had studied about the aspects of the areas about which we study in electrochemistry. That is, either the reactions involved to generate electricity or using electricity to conduct a or perform a chemical reaction like electrolysis or electroplating. So in that due course of discussion, we had also studied about the principal construction and working of galvanic cell, Daniell cell or voltaic cell, in which we had seen that there were electrodes which were metallic and there were electrolytes which were the corresponding salt of the electrodes. When these electrodes were connected with the help of a conductor, then electron flowed from anode to the cathode, because anode has tendency to lose electron and get oxidized, and cathode has tendency to gain electron and become reduced. So reduction takes place at cathode, which we draw in the right side, and oxidation takes place at anode, and that we write in the left side. So we had found out that the net EMF of the galvanic cell, in which zinc was dipped in zinc sulfate solution and copper was dipped in copper sulfate solution, was 1.1 volt, and that was found out by the value like this: E cell, which kind of cell, in which this couple was involved. This shows the phase difference. The phase means the electrolyte and the electrode. This double slash shows salt bridge. Cu2 plus shows the phase. Single slash shows the phase difference. Cu2 plus 0, 0, and these were 1 molar. In this kind of cell, at standard condition of temperature and pressure, the net EMF was found to be E right minus E left, or E cathode minus E anode. By convention, anode is always taken to be standard hydrogen electrode, but here anode is zinc sulfate. So this is anode standard, in which cathode is Cu2 plus becoming Cu and anode is Zn2 plus becoming Zn. Now the value of this we find from a table which is called as electrochemical series. Electrochemical series. In electrochemical series, the values are given in terms of voltage, in which the value of this was found to be 0.34 volt, and value of anode electrode potential or reduction potential of anode was found to be minus 0.76 volt, and the net EMF of the cell in standard condition was 1.1 volt for the galvanic cell. Now the question arises, how do we get the value of half cells or individual electrodes? So today we will be discussing about measurement of electrode potential of half cells using standard hydrogen electrode. SHE stands for standard hydrogen electrode. So the reduction potential of standard hydrogen electrode is considered to be 0.00 volt, and it consists of a glass vessel in which 1 molar HCl is filled in, and hydrogen gas is allowed to enter into this solution at 1 bar pressure, and one electrode made up of a platinum wire which ends with a platinum plate and which is granulated with granular platinum, which makes it platinum black, is used here. So this increases the surface area and hydrogen remains adsorbed in the platinum plate. So it is said, or it is considered, that the electrode potential of hydrogen for the cell in which H plus tries to become H2 when electricity is passed through it is 0.00 volt, and it is always treated as an anode, so that when we couple it with any test half cell, if we have to find out, or if we have to measure the electrode potential of any half cell, then that half cell would be a test half cell. And say if we have to find out the electrode potential of copper dipped in copper sulfate, this is copper dipped in copper sulfate, aqueous, and 1 molar, of course, because we are finding it in terms of standard condition. So standard hydrogen electrode is set up at 1 bar pressure and 298 Kelvin, and hence it is called as standard hydrogen electrode. So when we couple the standard hydrogen electrode with any of the half cell, and if we measure the EMF of the cell with the help of any voltmeter here, if we put a voltmeter over here, then we will see that the voltmeter will give a value of 0.34 volt. So this is determined experimentally, or it is measured experimentally. Now, based on the theoretical discussion which we had in our previous discussion, we know that delta E cell at standard condition is equal to E right minus E left standard, or E cathode minus E anode, and anode is always the hydrogen electrode, so that the E cathode which we get in terms of reduction potential of the electrode, and this value we get a measured value. This value is a measured value. We will put the net EMF of the cell is equal to 0.34 volt is equal to E cathode, that means Cu2 plus Cu, minus value of E anode is equal to 0.00 volt. So very clearly, whatever value will come in this voltmeter will be actually the reduction potential of the electrode, which we are testing by coupling it with hydrogen electrode. In this way, many cells are coupled here. So here we had coupled Cu2 plus Cu. Then similarly we can couple zinc 2 plus Zn, and we will get a value of 0.76 volt. Here we got 0.34 volt. Similarly, many such electrodes reduction potential is found out. These are reduction potential value. and they are charted in a table called as electrochemical series. So today we had discussed about standard hydrogen electrode and its application. A small question for you to practice would be like, if I ask you to describe how can you find E standard Mg2 plus Mg reduction potential. So to describe, what you have to do? To describe, you have to draw the diagram which I have drawn. What changes will you make? Instead of Cu2 plus, you will write Mg2 plus. Instead of Cu electrode, you will take Mg electrode. Instead of taking CuSO4, you will take MgSO4 or MgCl2. And then you will see the value of Mg2 plus Mg from the electrochemical series, and the same value you will put here in the voltmeter, because anything subtracted by 0 remains the same. That is the trick which we are using here by using simple hydrogen electrode. So this was about simple hydrogen electrode, which we use for finding out the reduction potential of any half cell. So half cell's electrode potential or reduction potential is found out by using standard hydrogen electrode. So this was all about it. Now you will see, so far we were discussing about all the electrolytes whose concentration was 1 mole. This seems 1 mole. This seems that if we change the concentration or temperature, that means the net EMF value or the net EMF value of the cell will be different. Such kind of cell is called as concentration cell. So we will be seeing how with the change of the concentration and temperature, the net EMF of the cell changes, and that will be seen in the Nernst equation in our next discussion. Thank you.